Good afternoon. I'm Marty Golubytsky, a professor of mathematics here at Ohio State and one of the organizers of this year's Science Sundays lectures. It is my pleasure to welcome you to today's lecture. This series of free public lectures on science interpreted broadly is now in its 9th year and is sponsored by the Ohio State University College of Arts and Sciences. It is, for those of you who may be counting, the 66th of these lectures, which qualifies it as one of the major outreach programs of the college. Usually introductions of academic speakers include items like where have they studied, or where have they held academic jobs, or possibly a list of their specialty areas. For today's speaker, Dustin Mixon, such an introduction would include items like he received his PhD from Princeton University. He's taught at the Air Force Institute of Technology. He's an assistant professor at Ohio State University. He studies interactions between algebra, geometry, combinatorics, and data science. You got all that? However, this list would not lead you to guess the subject of today's lecture. Every decade, politicians update voting districts to account for population shifts as measured by the U.S. Census. Of course, partisan politicians are inclined to draw maps that favor their own party, resulting in partisan gerrymandering. Part of what Dustin does is to explore how tools from mathematics can help deter this kind of political threat. Given this topic, it is perhaps not surprising that Dustin's introduction might include an additional item. Where has his work been quoted? Answers include places like Spectrum News One, Quantum Magazine, New Scientist and Forbes. Very unusual for mathematicians. Join me in welcoming Professor Dustin Mixon, whose talk is titled The Mathematics of Partisan Gerrymandering.
I'm turned on now. Can you hear me? Very good. I'm Dustin. I'm going to talk to you about gerrymandering. This slide is a little misleading. I'm not going to talk about the mathematics. I'm going to talk about some of the mathematics, okay? I'm not that full of myself. Okay, so let's start with an introduction. Okay. So there's a House of Representatives, the lower chamber of the legislative branch. They consist of 435 people, okay? Each of those people doesn't represent an entire state. It represents a portion of a state, a voting district, okay? This map color codes the different voting districts. You can see that some states consist of one voting district, like North Dakota, and then others have lots of voting districts, like California. The districts are distributed amongst the states according to population. So if a state has more people in it, they get more districts, okay? This is measured by the census. And populations don't stay stagnant. They move across the country. So whenever you have a shift in population, that's going to be detected by the census. Every 10 years, we make a census. And that information is passed to state governments, who then are told how many representatives they get this time. And then they also use the census information to decide how to chop up their state into voting districts, okay? So that signal comes from the census. And that signal also informs how districts are cut up for like state government type stuff, okay? And there's a similar story there. Okay. So the dream is what is called partisan symmetry. We would like these districts to do a decent job of representing the interests of the people. Okay? So you could imagine that if on the whole scale, you count what's the proportion of votes that, I don't know, such and such a party got, maybe that would reflect somehow the proportion of seats that are won by that party. Okay? So the dream would have something like 50% of the votes leads to 50% of the seats. And it increases and decreases from there. Okay? That's the dream. That's what we would like. So Elbridge Gerry. This is one of our founding fathers. Okay? He signed the Declaration of Independence. He was a governor of Massachusetts. He was even one of the first vice presidents of these United States. But you don't know him from those accolades. What you know him from is gerrymandering. Used to be called Gerrymandering because his name's Gary, but English. Okay. The main idea of gerrymandering is to manipulate these voting districts in a way that benefits you or your party or whatever. Okay? You want to get an advantage by messing with boundaries. So let's look at a cartoon. Imagine this is a state, and the north part of the state is very red. The south part of the state is very blue. Okay? And let's say that we have the task of breaking up these square precincts into districts of equal size. Okay? But we know that the north side is red and the south side is blue. We know this because of like prior election data, stuff like this. Okay? We want to exploit this side information to gain an advantage. So if I represented the blue party and I had the opportunity of drawing lines for voting districts, I might do this. So this is doing a move called cracking. We crack the red vote across a bunch of different districts so they don't accumulate enough voice to get a seat. So you'll see this first district has a majority blue, so we're going to win that first district. Blue will also win the second district. Blue's going to win all of the districts because blue had the pen. They will make the map in a way that gave them an advantage. This is gerrymandering. What if red had the pen? If red had the pen, red can also score an advantage. Used to be red has only 40% of the vote, and they're able to get 3 out of 5 districts, 3 out of 5 seats by drawing these contorted voting districts. So this is one of the districts, this weird U shape, okay? There's one red precinct, and the rest are blue. Total of 10 squares. You need 10 squares to have this equal amount per voting district. But they're packing all of these blue votes into a single district. They're packing all the blue votes into this other district, and then they're cracking the remainder across 3 voting districts. They end up scoring 3 seats from this procedure. Okay? If you wanted a proportional outcome, like maybe you didn't represent red or blue, you just wanted democracy to work or something, then what you might do is instead of doing like columns or something, just do rows, right? Just first row is a district, second row is a district, third row is a district. You end up with the same number of seats, same proportion of seats as the proportion of votes. That's gerrymandering. And this is just a cartoon of gerrymandering. Gerrymandering is alive and well. So this is an example of a gerrymandered map. This is North Carolina. Red receives 50% of the vote, and they get over 3/4 of the seats. What you do is you pack Charlotte into a district, then you pack Raleigh in with Chapel Hill into a district, and then you pack Durham and other smaller urban areas into a district. There's also some blue around here, blue voters, but you crack them into red districts. You get 10 out of 13 districts this way. Okay? North Carolina. Here's Pennsylvania. This map is interesting. It was proved in Pennsylvania State Court that if you wiggle the boundaries just a little bit, no matter how you wiggle them, the results completely change. This is finely tuned in order to get this outcome. Okay? So that's interesting. These two examples were for US congressional districts. This is for the Wisconsin State Assembly. This is actually this was the subject of Gill v. Whitford, recent Supreme Court case. And yeah, you're able to score north of 60% of the seats from less than half the vote. You're seeing a lot of red on the screen. I don't want you to get the conception that this is a Republican problem. This is both sides. There's bad actors on both sides, okay? So just keep mindful of that. That's what's going on here. Okay. The perspective of this talk, the perspective that I have, the perspective that some other people have, is that gerrymandering is a threat to democracy. Okay? The perspective is that the citizens in a democracy should be selecting their representatives, not that the representatives select the people they represent. Okay? So whether you're blue or red, doesn't matter. Don't gerrymander. Okay? And this perspective is important, especially right now. The next census is just around the corner. And we need to be aware of what sorts of tricks are available to do gerrymandering. We need to be able to identify it. We need to be able to prevent it. Okay? This is urgent. So in this talk, we're going to break out into 3 parts. First part, I'll talk about district shapes. Then I'll talk about votes versus seats. We'll think more about this partisan symmetry, that S-curve we saw at the beginning. Then we'll talk about redistricting protocols. FYI, the first 2 parts are going to make you sad. Okay? So just calm down. You're going to be sad. But then, the third part, you'll receive some hope. Okay? Okay. And we're going to start with shapes. So there's a long history of pointing out gerrymanders by virtue of their shape. In fact, in the first gerrymander we've ever thought to point out comes from Gerry. He approved this when he was governor of Massachusetts. And the local newspaper made a political cartoon out of the voting districts. They drew one of the districts as the profile of a salamander, which is the mander part of gerrymander, okay? Yeah. Okay. But even today, our newspapers are showing us how these bizarre shapes are all over the place, and this is bad. So I want to kind of give away a little bit of my punchline early on, just so you don't get upset with me while you hear me talk. These shapes are easy to poke fun at. That's why they show up in the newspaper. They make for good graphics. But it's not necessarily a good detector of the problem. Okay? In fact, it could be counterproductive to zero in on the shape as the bad thing. Okay? But let's poke fun. Okay, so here's a district whose boundary is so out there that you can design a 5K run around it, and you have to make random turns. Like, why am I turning here? Who lives here? That we need to make sure that they don't live in this district or this other weird thing. Okay, so This is good outreach or whatever, making sure people are aware that gerrymandering is a problem. We can make fonts, computer fonts, just using weird shapes. I don't know if you can read this. It says Science Sundays. That's what we're enjoying right now. Okay. So there's a website, you Google it, you find it. And you can like type in whatever, and it makes this thing, and you can tweet it. Okay. So how can I tell if something looks weird? How do I know if something's a bizarre shape? I'm a human. I can look at it and say, yeah, that's bizarre. This is so North Carolina. Okay, so that map in North Carolina I showed you wasn't the first stab they had in the last decade to draw a map. It keeps getting thrown out by courts. This was an earlier district, and it looks weird. It like zigs and zags. The fact that you're wasting so much perimeter in order to capture this area, this voting district, is a feature that people use to quantify how bizarre a shape is. And this feature dates back to antiquity. So there's this book. It's called The Aeneid by Virgil. And there's this character named Dido. And Dido, she did something noteworthy. So she goes to this place she's never been to before, and she's thinking, I'd like some land. Okay? So she finds someone with land and says, I want some land. And they like haggle or whatever. And she says, you know what? I'll give you this amount of money, and I'll take whatever land that I can encircle in the skin of a bull. Sometimes it's an ox, right? But the skin of a bull. Okay. The person she's talking to is, yeah, sure. You take the skin of a bull, you're gonna get like this. Sure, great, easy. And then Dido, she's clever. So she instructs someone, I don't know if you can see this very well, she instructs somebody to cut the skin into really thin threads, okay? And then tie up all these threads to get a huge string, okay? Now she's going to use this string to encircle some land, okay? She wants as much land as possible. How does she do this? So this is what she does. So this is water, and that's land. She takes one end of the string and puts it on the coast, puts the other end of the string, another part of the coast, and then she makes part of a circle to enclose some land, and she tricks the guy, gets all this land. She founds a city called Carthage. She becomes the queen of Carthage. Okay. So she zeroed in on a feature, and that is that circles are particularly efficient at enclosing area. Okay, these are two shapes, circle and square. These have the same perimeter, but you see the square sweeps less area, right? Somehow the square, the perimeter isn't as efficient as the perimeter of the circle. And it took some time for mathematicians to get this right. There's this thing called the Isoparametric Inequality. It's a thing that after seeing that circle and square, you might think, yeah, that's probably the true inequality. You figure out what it is for a circle, and then you generalize. I'll tell you, there's an interesting history of math lecture roped into proving this correctly. Mathematicians keep getting it wrong. They finally figured it out, but there's a difference between conjecture and a theorem. This is a theorem right now. So given any region in the plane, okay, like a square or a circle, I want you to think of the area. That's a number, call it A. I want you to think of the length of the perimeter. That's a number, call it L. Okay? Now I want you to do some things to A and L. I want you to multiply A by 4 pi. You remember pi. Just think about it. Okay? 3.14, whatever. Okay. So multiply A by 4 pi. And then I want you to take L and multiply it by itself. Take L squared. And it's always going to be the case that 4 pi A is less than or equal to L squared. Okay? Furthermore, the only way that those two numbers are going to be equal as if the shape you started with was a circle. Okay? Isoparametric inequality. So this is some math speak that kind of tells the story that these pictures give you, right? The shape that sweeps out the most area for a given perimeter is the circle. Okay? So after mathematicians figured this out, some political scientists got wise to this. They wanted to defeat gerrymandering by detecting gerrymanders by their shape. They came up with a score, the Paulsby-Popper score. What they do is they take the number on the left and they divide by the number on the right. This number is the biggest when you have a circle. The number is 1 when you're a circle. It's the smallest when you don't sweep out any area. You're just like there and back, you know, like you're using nothing but arc length to get no area. So let's look at examples. So this is quantifying wasted perimeter. Big number's good. Okay? So the Paulsby-Popper score of a circle is 1. It's the biggest number you could have, according to the isoparametric inequality. Big number's good. How about a square? Well, it's dipping a little, but it's not really small. It's just like 0.7 something. Okay? How about a triangle? There's more zig and zag to a triangle. Well, it's getting smaller, 0.6 something. How about one of those districts that we like to make fun of? Like, let's look at the Science Sunday as a U in it. Let's look at the U of Science Sunday. 0.05, okay? Way small. So Paulsby-Popper is doing a decent job of giving a number to your gut reaction, right? Okay. There are some problems with using shape as signal for a gerrymander, especially for a partisan gerrymander, okay? Let's talk about some problems, some issues. There's going to be false positives and false negatives. False positive is when you say it's a gerrymander when it's not actually a gerrymander. False negatives when you say it's not a gerrymander when it's actually a gerrymander, okay? False positives. Let's talk about the Coastline Paradox, okay? So what is the perimeter of Great Britain? Okay? It depends on how long your ruler is or something. How long is the shortest distance you're willing to make everything in terms of. So if your shortest distance, if you're measuring in 2.8 kilometers, that's your unit, then you get a certain distance. Nope, this is 100. The length of this ruler is 100 kilometers. So you get one distance, 2.8 kilometers. What if your scale is 50 kilometers? Well, I'm zigging and zagging more, so I get a larger perimeter. If the length of your ruler is 100 meters, that's your scale, then it's much bigger. This is going to happen whenever your state has like a river as a border, or like a coastline, like an ocean or something. So you could imagine like Ohio has a river underneath it, right? So if you try to redistrict Ohio, you're going to have some districts that touch that, and all of a sudden that river is contributing to your Paulsby-Popper score. That's not fair. That doesn't make any sense. False negative. False positive. Coastline paradox. Here's another one. Okay, this one's more subtle. So this is the letter U in Science Sundays. If you have north be up, then it's a U on its side. Okay? Okay. So the story here, this is not the result of a partisan gerrymander. This is the result of something more subtle. Nobody in this area is upset with this shape. Okay? This was specifically drawn to give these two communities, these are Hispanic communities that they wanted a representative to represent their culture. So they made do and did a thing. Everyone around here is blue, and they just wanted something that represented their culture better. And for that reason, I would say that Paulsby-Popper is a false negative here. Like, it's a really small score, but it's zeroing in on the wrong thing. It's a strange shape, I agree, and there's a reason for that. We'll see more instances of weird shapes being useful later on, okay? Let's talk about false negatives. So a ham sandwich is not a false negative. I'm bringing you down a story, so just bear with me. If you're confused why there's a ham sandwich here, just calm down, you'll understand in a moment. First, I need to explain to you what the ham sandwich theorem is. Okay. So if you're like me, you like your ham sandwich to be cut up into 2 pieces. You also like each piece to have exactly the same amount of bread, exactly the same amount of cheese, exactly the same amount of ham. Okay? Turns out you can do that. You can always, if you have ham, cheese, and bread, there's always going to be a way to cut it to simultaneously split all 3 of those in half. Simultaneously. Okay? The ham sandwich theorem is a lot more interesting than that. So suppose your enemy takes the ham sandwich and throws it in the air. So the bread goes one way, cheese goes another, the ham is spinning right here. Okay. Let's pretend that I'm Neo from the Matrix. Okay? And I freeze time. So now bread, cheese, ham. It's possible for me to take a samurai sword and cut all 3 of those at the same time with one swoop, not some interesting swoop, one straight swoop that cuts all 3 of those exactly in half. Okay? That's the ham sandwich theorem. The fact that there exists a way to cut all 3 at the same time. This has consequences to gerrymandering. The 2-dimensional version of this problem, of the ham sandwich theorem, says that whenever you have 2 sets, okay, in this case I have a set of red spots and then I have a set of blue spots, okay? Whenever you have 2 sets, there exists a line that cuts the red in half and simultaneously cuts the blue in half, okay? So how would I do it? Straight line, nothing fancy. Straight line. So I worked ahead. Here's an answer. Okay. This is something you might be able to prove to yourself at dinner tonight. Like this one isn't that hard. It's quite fun to find how would you get a line in general. Okay. So think about that. So imagine if right here I have a total of 8 blue and a total of 8 red. If I had like 10 red and only 6 blue, and I cut both sets in half, that means both sides have just a slight majority for red, right? So you can gerrymander with straight lines. I did this. So this is based on 2016 election data. So we use that as a proxy for whether people are red or blue. And you can iteratively cut Wisconsin in half. And you keep cutting it in half, so Trump won Wisconsin, so I can make that every district is red using this process. And it turns out you can make it almost all blue as well. This is not a consequence of ham sandwich. I don't understand why this is possible. But it's scary though. So you can't get all blue because that would mean that the popular vote was blue. Popular vote wasn't blue, and still you can give blue 7 out of 8 districts here, okay? So you can gerrymander with straight lines. This would not be detected by Pulsby-Popper as a gerrymander. So that'd be a false negative. And so the ham sandwich theorem produces some depressing results. And you don't even need a ham sandwich theorem. Like this is an example where all of the districts have a respectable Popper-Pulsby score. And so shape detection for a gerrymander would not flag this as a gerrymander. And yet it's packing and cracking like crazy, okay? So maybe shape is the wrong thing to zero in on, okay? What else should we use? This is the second half. Okay. Votes versus seats. So I'll remind you the dream. The dream is that I get a curve like this. If 50% of the people vote for a party, then they get like 50% of the seats. If there's more than 50, they get more seats. Fewer, they get fewer seats. So this is, and it's more than just the fact that the curve is increasing. There's a symmetry. That's the symmetry part, partisan symmetry. If blue gets 60% of the vote, then they get a certain number of seats. If red gets 60% of the vote, they get that same number of seats, okay? It's symmetric. So you would like your districting, the way you cut up your state into districts, you'd like it to have a nice S-curve, to have this partisan symmetry. You're not going to be able to tell, okay? So just given a districting, you can like play with data, like model how people vote and like get a model. Maybe it looks like an S, maybe not, but the court isn't going to care about your model. They're going to call it counterfactuals. They're not going to believe it. It's not going to hold up, okay? So we want this thing that we can't attain. There are things that we can measure, things that we can actually detect. We can detect maybe whether the S-curve is a straight line through 50-50. This is called proportionality. You want, if you get 50% of the vote, you get 50% of the seats. If you get 70% of the vote, you get 70% of the seats. That could be a dream. That's called proportionality. The Supreme Court has already chimed in and said that that's an unconstitutional request. That's too hard of a request. So proportionality, you can measure it, because you can look at election data and measure how many votes and seats there were, but not good enough. Another thing you can quantify is you can try to point towards or quantify like packing and cracking. Like if the red vote is cracked across multiple districts, you'll see that there's a bunch of people in this district that voted red, and it didn't result in a red seat. Also in this other district, a lot of people voted red, didn't convert to a seat. You can count how many times you got a bunch of votes that didn't convert. You can calculate all these wasted votes and use that number. There's a tidy metric called the efficiency gap that mashes all these numbers together. And a big efficiency gap says you're bad, and a small efficiency gap means you're not necessarily bad. And the Supreme Court said, I don't know about this. They said, let's punt. You didn't establish standing, is the legal speak. So people come up with these things that you could actually measure, and the courts don't like it. I'm going to talk to you about something even simpler. So I'm not going to ask that a bunch of votes are wasted, or opposite of that. I'm not going to ask that we don't waste many votes. I'm not even going to ask for proportionality. I'm going to ask simply, can I make it where if my party gets at least 49% of the votes, then my party gets at least 1% of the seats? Okay? That's all I want. Let's say that's all I want, for the sake of argument. Let's see what happens. Also, I want my districts to not look weird. Remember that U shape, how it was 0.05 Popper-Pulsby score? Let's ask for it to be at least 0.01, okay? I'm not asking for much. Also, the Constitution says that the districts need to have the same number of people. So we're going to ask that the districts have roughly the same number of voters in them, okay? So I just did a move. Did you catch it? I started talking about people, and then I talked about voters. Those are different things, right? Yeah. It turns out that all you have to ask for is that on both parties, the proportion of people that voted is not equal, but close enough, okay? Like this is close enough to 1. You know what I mean? Like, that's all I need. Okay. Okay? So I want to satisfy the Constitution. I want none of my districts to look too weird. And I want non-trivial representation. If you get 49% of the vote, I guarantee you get at least 1% of the seats. You can't ask for that. That's too big of an ask to ask for all 3 of those simultaneously. Okay? So we're getting sad. Great. So this isn't to say that that it's impossible to achieve in a real-world map. Okay? That's not what this is saying. This is saying that it's possible for the voters to live in places while having a political affiliation in such a way that you can't satisfy all 3 simultaneously. So there's no districting system that's robust to how the voters choose, like where the voters choose to live. Okay? The way you prove this theorem is you devise this adversarial way for voters to live. Let's say that the Republicans and Democrats, they peanut butter spread themselves across a state, okay? And by that I mean, like each of these, this is kind of an eye chart, I'm sorry. Each of these squares, I'll tell you so you don't have to look at it. Each of these squares has 5 blue and 4 red, okay? Each of these squares has 5 blue and 4 red. So this is an extremely homogeneous mixture of red and blue across the state. By doing this, let's say I were to draw a district that didn't look weird, okay? Since he doesn't look weird, that means that if I look at all of the squares that he touches, most of the squares are not cut through, okay? The ones that are cut through are the ones that the perimeter sees. But if I have a lot more area than the square of my perimeter, then most of the squares that my district comes in contact with are unharmed. So you still have that most of the people in your district are blue. And that's what happens here. You inherit the statistics of these small squares, okay? That's what happened here. I tried to draw as best as I could districts where all of the Pulsby-Popper scores were large, and that's what I got. And then I wanted to convey, well, what if I tried to make it so that the proportion of red to blue matched the votes? You know, I wanted the seats to be close to the votes. And what I did was I drew this map by hand, and I felt bad doing it. Okay? These aren't real people, but in order to make a district, I needed to get all of these reds in a common district so they had a voice. And it felt really weird. Okay? So that's probably because I've grown up to think that bizarre shapes are bad. I don't know. Okay? This comes up in the real world, not just out of a mathematician's head, okay? So Massachusetts, if you look at the vote, 30% more or less is Republican. And then when you look at all of the US congressional seats, they're all Democrat, okay? The reason is that the Republicans are peanut butter spread across the state. We don't consider this to be a gerrymander. All the shapes look nice. Massachusetts isn't. It's no North Carolina or Pennsylvania. There's a political geography component going on here. Okay? Okay. Sometimes it's not impossible. Maybe most of the time it's not impossible. Sometimes, even if it's not impossible, it's extremely hard to find a fair map amongst all of the compliant maps. So just to give you a sense of how complicated the set of compliant maps can be. These are the rules that the Wisconsin State Assembly has to satisfy when they do redistricting. They need one person, one vote. They need their Paulsby-Popper score to be at least, that's a respectable number. They need to satisfy the Voting Rights Act. There's some history that certain districts aren't allowed to change. There's lots of constraints that they have to satisfy all at the same time. And it can be difficult to thread the needle, like figure out how do I satisfy all these constraints and still be fair. So you can prove a theorem to this effect where we have a similar notion of compliant map as to the impossibility theorem. So I ask for one person, one vote. I also ask for a reasonable notion of compactness. This one isn't Paulsby-Popper, it's something else, but it's reasonable. And amongst all maps that satisfy those two things, I'm trying to find a map where if you get 49% of the vote, then you get 1% of the seats. So if I give you a map and you try to find a fair map amongst compliant maps, you're going to have a hard time. So in computer science, they would say that this problem is NP hard, which is a notion of how hard it is. Here's a good way to tell you how hard it is. If you could solve this quickly, then you can break all of the cryptographic ciphers. So you could, if you want to hack into E-Trade or something, then you can write code that uses this as a subroutine. And if you can quickly solve this, then you can quickly hack, okay? So the thinking of the times is that, no, you can't crack these ciphers quickly. Those are actually hard. We don't know that for sure yet, but that's the thinking. And as long as we believe that, we have to believe that this is equally hard, okay? So as long as you're putting money online, you have to agree that this must be hard. Yes, sir? So the locations of the voters are real numbers. So testing all of the digits is not something you can do in finite time, but you can still restrict to a class where they have terminating decimal expansions, and then that sub-instance would be NP complete, yeah. But since the voter locations are allowed to be at like pi comma e or whatever, we say NP hard, but yeah, good question. So both the impossibility theorem and this NP hardness thing, these were looking at worst case scenarios of where the voters could possibly live relative to how they vote. So this might not reflect all of the real world maps we encounter in practice, but what it does tell us is it tells us what we can't expect our redistricting protocols to be able to do. We can't expect redistricting protocols to be able to satisfy everything we ask it to satisfy necessarily, okay? But what can we ask for? Okay, that's the subject of the third part. Okay. This is where we start to get happier, okay? Good question. Okay. So we're going to look at a couple of protocols. First protocol, the shortest split line algorithm. So the way this works is we're not even going to pay attention to whether you vote blue or red. We're just going to draw the map in a way that's the least gerrymandered looking as possible. We need to cut up Maryland into some districts. So I'm going to cut up Maryland using a series of line segments. So I'll look at all possible line segments that break this state up into two equal parts population-wise. And then I'll look at the particular choice of line segment that's the shortest possible. Okay? So the shortest line that accomplishes that is right here. Okay? Okay. Actually, it's right there. There we go. That makes more sense. Now, once you cut that up, you're going to repeat the process for the halves. So for the top half, I'm going to find the shortest line that splits it in half. It's this guy. And the shortest line that splits the other in half. And you repeat that. So by looking for the shortest line, you're trying to maximize the Paulsby-Popper score. This is the algorithm I used in the middle panel from my impossibility theorem. And so there's a problem where you're not paying attention to the political geography. And so you might accidentally gerrymander in favor of one party over the other. Okay? So that's the first example. For the second example, I need you to think creatively with me. So I want you to imagine that you find yourself in charge of these two kids. Okay? And despite appearances, these are brats. Okay? And there's some cake in front of them. They both want the same amount of cake. Okay? So if you're a naive babysitter, you might try your best to cut the cake in half and then give it to them. But invariably, one of the brats is going to whine that the other is slightly bigger than theirs, and the other doesn't want to trade. So that's not the right solution. What you should do instead is give the knife to one of the kids and tell him not to stab the other kid. Instead, that kid is in charge of cutting the cake as best as he can in half. And then the other kid gets to pick which of the two halves they eat. Okay? This is like a King Solomon type of thing. Okay. Recently, some folks figured out how to transfer this trick to the redistricting problem. Okay? So this solution for cake is called I cut, you choose. For redistricting, it's going to be I cut, you freeze. Okay. So here's the game. You have two parties. Maybe you think of them as brats. Okay. And they're going to take turns drawing a map. So the first player is going to draw the map that he likes into K districts. Okay? He's happy with all K of the voting districts that he draws. He takes his map, he passes it to the second player. The second player then looks at the K districts and decides, okay, I'd be okay making this one an actual voting district. So whatever map we end up with, this is going to be one of the voting districts. Okay? And then he erases the other lines and draws his own map, so districts of his choosing. And he passes that map to the first player, who then freezes one of the voting districts. This one is definitely going to be a district in the final map. And they go back and forth. You end up with a map. Okay? I cut, you freeze. So there's a theorem that says this works well. So there's the theorem, it factors out geometric constraints. So it doesn't require that when you draw the districts, it doesn't require that the districts are connected, let alone they have a large Popper-Paulsby score. It just, you cut up the districts, the map into districts. No geometric constraints. If you play optimally, then you'll end up with a really nice S-curve when the number of districts gets large. Okay? This is interesting. Think about what happens in the game if the number of districts, if K equals 2. The first player draws a map, passes it to the second player. I guess I'll freeze this one. There's nothing else to draw. Pass it back. Great, I'll freeze the second one. We're good. So this is the same as the first player gerrymandering. This is obviously unfair when K equals 2. When K equals 3, it's slightly less unfair. It's slightly more fair. But it's when K is like 20 or something that it's good. So We want to remove this first player advantage, okay? And that's the intent of this new thing we have called utility ghost. Okay, utility ghost. So I have two parties, they're going to play a game. Okay, there's a map. Let's say the state has 6 precincts, and I need to break this up into 2 voting districts. In this game, player 1 tells the top left precinct to be in voting district 1. I don't know what voting district 1 is going to end up looking like, but I do know it'll end up having that top left precinct in it. Okay? That's the first move. Second player responds by sending the bottom left precinct to the second voting district. In the end, we're told that there's going to be 2 voting districts. So each of them has determined that one precinct is in the first one, another one's in the second one. We don't know what the rest of the map looks like just yet. The first player responds by sending this precinct to the second voting district, etc. Okay? In the end, you get a breakout of your precincts, in this case into 2 districts. You got 1 and 2. 1 is majority red, and 2 is majority blue. Okay? This is achievable in the real world, but you have to add an extra thing. So when you make a move, you have to demonstrate to the other player that it's possible to complete this map to something that's compliant. Okay? With the way precincts are assigned to voting districts right now, it's possible to end up with contiguous districts that have good scores or whatever. Okay? So that's an extra thing. And we have a theorem that says if you have enough precincts to go around so you can make enough moves, there's no geometric constraints here. Optimal play is going to produce an equitable map. Okay? We require an extra hypothesis that we have partisan balance. So we start off having the same number of red precincts as blue precincts. Okay? We don't think this is necessary. We observe in practice that we get beautiful S-curves even without that assumption. Okay? For example, well, this isn't practice, but we're getting closer to practice here. So let's pretend our state consists of 10 precincts, and we have to split it up into 2 voting districts. And let's say the geometric constraint is that both districts have to be connected. Turns out there's 7 ways to do that in this case. Those are the 7 possible maps. 7 possible ways of breaking up the state into 2 districts. If you were to randomly decide whether precincts were red or blue, and then draw one of these 7 maps at random, you would get a nice S-curve. If instead of drawing a map at random, you played utility ghost optimally, then you also get a nice S-curve. You get this no matter who plays first. Okay? If you play I cut you freeze, or equivalently ask the first player to gerrymander the map, then you get these wonky S-curves. Okay? As soon as you get slightly more than half, this is a guy gerrymandering. As soon as you get slightly more than half, you get all of the seats. Okay? Okay. New Hampshire currently has 2 districts. So you could imagine trying to play this game to draw those districts. We're going to ask for each voting district to be comprised of 5 counties. Actually, not necessarily 5 counties, just counties. And I want it to be, each of them to be connected. I'm also going to ask that the 2 different districts have the same population to within 10%. Okay, this is 1 person, 1 vote. Okay. If we think of the presidential election returns as the truth for what is red versus blue. You see that the vote is remarkably close in that state. And even despite that, there's a compliant map that gives both seats to the Democrats. Okay? If you play utility ghost, both sides play optimally. It doesn't matter who goes first. You're going to get one of the other maps, so not all blue. Okay? Okay. So I spent the first couple of parts of my talk conveying to you that shape is not the right thing to zero in on for gerrymandering. Okay? You can gerrymander with nice shapes, thanks to the ham-sandwich theorem. Sometimes you need to use strange-looking shapes in order to accomplish a fair end, fair redistricting. Sometimes it's difficult to find a fair map amongst compliant maps, even if it exists. Sometimes it's hard. I showed you some redistricting protocols. It looks like you can have a bipartisan protocol that delivers a nonpartisan outcome. So even though both parties are trying their best to gerrymander in favor of their own party, they accidentally represent the people. We'd like some theory to explain the S-curves that we observe, even when we constrain the geometry. We'd like to understand ulterior motives. So what if I'm playing utility ghost, but secretly I want a district that's good for me personally, like protecting incumbents? Or maybe I want my two enemies to have to compete for a seat next election, something like this. How does that factor into the game theory? Also, the artificial intelligence is getting scary good at games. So they can play, the computers can play Go better than any human right now. Thanks, Google. Okay. What you could do is maybe both parties want to play utility ghost, but maybe one side is self-conscious about how good they are at playing the game. So they'll just give their game playing to a machine. Like, the machine's going to be playing better than a human anyway, so we'll play so that they can beat our opponent. And then the other side has the same idea, and now you're just allowing the machines to take over our democracy. Maybe that's not a good idea. I don't know. But that's my talk. Thank you very much.
Fantastic talk. Are you willing to take a few
Yeah,
questions?
definitely.
I just want to remind you, before we go to the questions, that we'll have a reception upstairs in the starters room. And if you would like to get your chocolate first, go quickly upstairs. If you want to hear some more about the questions, you can stick around here. That's a voting paradox, I think. Okay.
Great.
Can you bring a microphone around so we can all hear?
You're talking about the districts where you can like make a 5K route with them.
Yeah.
But with 5K routes, they almost always loop around, which is really irritating because sometimes you forget which way to go. Mm-hmm. I run cross country.
Yeah, I haven't organized one of these 5Ks. I just saw it in the news. I think when I looked at the map, I think there was, I think that this is a turnaround point maybe, so they don't have to go all the way around. But it's definitely, they're begging to get lost right about here. Or maybe cheat and not, not make the turn and get to the finish line sooner. Yeah, presumably they had like lots of signage, maybe people giving out Gatorade at those turning points just to just to make sure they stay on track. Good question.
With the Supreme Court decision, the latest Supreme Court decision, leaving it up to each state
Yeah.
to take care of their own redistricting. Let me start over. With the Supreme Court decision to leave it up to the states to make their own decisions pertaining to the district lines being drawn, already unfair, how difficult will it be to make this thing right, if it ever can be?
Yeah. So I predict, so first of all, I'm not a legal scholar. I'm not a political scientist. Okay. I'm a mathematician. But you're asking me, so I'm giving you my answer. I predict that things will change when a narrow window of opportunity presents itself. So it has to be right around a census. It has to be when the party of power perceives a sea change is looming. And so they institute some sort of bipartisan redistricting commission so as to save themselves after the election. That's a case-by-case basis. So what fraction of the states will do that? I have no idea. Mm-hmm. Yes, sir.
The question I had was in the situation like we have some states or some districts that are very red, some very blue. We get people that get disappointed and they don't vote, because they figure it's not going to count.
Mm-hmm.
So we're always balancing the population versus voters. But do we really know who the voters would be if they felt their vote would count? And that's the question. How do we deal with that in the mathematics? The uncertainty, take that into account.
Right. I would be interested in any polling data that doesn't filter responses out based on whether the pollster thinks that they're going to vote. When I read polling data, the first question is like, are you going to vote? And if the answer is no, they don't ask the next question. So I have no idea it's a known unknown, so to speak, right? And how do you account for that? That's a great question. Yeah.
There's a governance issue that this doesn't completely address. One of the concerns has been that safe districts create more radical politicians because they can drive to each end. And is there any way to take into account making districts somewhat competitive rather than just safe districts?
Yeah. So competitive districts are more plausible when a state is already, like at a state level, it's competitive. In general, this polarization issue, there's another way to vote called approval voting, where on the ballot you say whether you'd be okay with each person being representing you, and the studies that I'm aware of suggest that when you do approval voting, the winners are the ones that are closer to the middle, so it counters the polarization problem.
So that's not a district.
It's not. I think it's easier solved by changing this majority or popularity wins kind of thing. So there's the microphone's over there. Great.
I'm a political scientist, and I was
Great.
one of the 5 negotiators who created Issue 1 in 2015.
Okay.
And there's some very good news about Ohio, and that is we did, in fact, follow your advice and take advantage of a moment of vulnerability on the part of the incumbent majority. We did create a bipartisan commission that will require 2 votes from the minority party out of the 7 members of the commission. And in one of the sections of the revised Constitution that goes into effect on January 1st, 2021, we institutionalized proportional representation.
Oh.
So this is the only state in the country that will require proportional representation as a criterion. Now, it is a second-rank criterion behind a whole series of county and city splitting limitations, but nonetheless, I think it goes a long way towards getting rid of gerrymandering, or at least constraining gerrymandering in Ohio.
Very good, thank you. I had some hands up from the front.
Hello. I was going to ask whether or not you've been in contact with or had your work be involved in any of the decisions by, either related to Ohio or other states or anything like that.
No,
whether or not that's been picked up.
It's gone the other direction where I've spent time being a political junkie online, getting upset and having it inspire my math. So whether it'll make a turn, time will tell. Yeah.
Why don't we just take one more question
Great.
and then we'll go upstairs.
Yeah, it's just a quick question. I wonder, why do you want to ask curve instead of a straight line?
Right. So it can be a difficult thing to ask for to get exact proportionality, and because there's what we observe in practice is something that I don't completely understand. In practice, if you look at actual votes in states that are not considered gerrymandered, if you look at, so you get 50 at 50, and if you look at the slope, for some reason the slope is like 2 instead of 1. So there's something happening that I don't completely understand that's somehow coded into political geography or something where we observe a slope of 2. And that's something that was baked into this efficiency gap metric that was part of the Gill v. Whitford case. But personally, proportionality is also an example of partisan symmetry, so I'd be happy with that as well. I'll remind you, my impossibility theorem just asked for 49% gives you at least 1%, right? So that's a completely different end of the spectrum, but I'll take what I can get.
Okay. Dustin, thanks so much for a spectacular talk.